logarithm. Natural logarithm, we talked a little bit about this. It is a special log. And if I write ln of x, it's really log base e of x. It's kind of like if I write y equals log of x. What's the base on log? 10. So natural log is base e. Common log, or it's called the common log. Natural log is base e, and then common log gets base 10. And if you forget who's what, take a look at your face on your calculator. Above log is 10 to the x. That says his base is 10, because that's the inverse function. Above natural log is e to the x. That tells you the base on natural log is e. So if you get confused, and any other time you'll see a base. So any other time you'll see a base. So if there is no base, or it's natural log, can't remember what the base is, take a look at your calculator. Calculator can actually help you with that. So this is not how your book graphs this thing, but this is still the way I would do it. It's the way we've done it all along. I would look at y as being equal to log base e of x. That happens to be what natural log x is. Or we know that x equals e to the y. So graphing just like you graph anything else. Right. So if I look at my t-bar chart, x equals e to the y. So yeah, I can put in y's and get out x's. So -2, -1, 0, 1, and 2. This would be e to the -2, which is approximately 0.1. E to the -1, you do enough of these, that's what happens. It's approximately 0.4. E to the 0 is 1. E to the 1 is 2.7. E to the 2 is 7.4. And I've done a lot of these between yesterday and today. So now I just go to my graph paper, and 0.1 is -2, and 0.4 is -1, and 1 is 0, and 2.7 is 1, and 7.4, so I'm out here someplace, is 2. And then you just connect the dots, and he looks like any old logarithm. All our logarithms have looked like that, have they not?
I have a question.
Mm-hmm.
How do you know to do it the opposite? Because haven't we usually been doing x's and getting out y's?
Because of the fact, well, in the case of natural log, you could put in x's and get out y's, but here's going to be your problem. If I wanted to say in graph x natural log x, what x's do I put in? I can't say -2, -1, 0, 1, and 2, because I can't take the log of a negative number. And I can't take the log of 0. So then what would I have to do? I'd start at 1. This is what your book does. 2, 3, 4. And then you take your calculator. And then a natural log of 1 is 0. Natural log of 2, I'm going to clear this, and so I move it up there. Natural log of 2 is 0.7. Natural log of 3, so that's what you have to do, is 1.1. Natural log of 4 is 1.4. Now, here's where your problem then comes in. At x equal 1, y equals 0, so I'm there. At x equal 2, I'm about 3/4. Of x equals 3, I'm slightly over 1. At x equals 4, I'm about 1.5. Now you really have to know what this thing does. Right? Now what your book does then, it says, well, I know this guy's going to go out, and I don't know what he does the other way. So then it says, okay, well, this is what I'll do. I'll put an x equal 1/2. So that's the problem when you're putting in x and getting out y. You have to know a little bit more about the graph, number one. And then secondly, if you get a piece of the thing, then you've got to say, what am I going to have to do to get the rest of it? Because there is more.
So
but it works.
Only when you're working with natural logs do you do the opposite.
You always do the opposite when working with any log. See, if I were going to, and this is what we've done before, if I wanted to graph log base 3, right? Don't have base 3 on my calculator. That's why we went to x equals 3 to the y, and then we put in y's and got all x's. So if you're going to graph any log, you want to end up rewriting it in exponential notation. You can get away with it with natural log because it's on your calculator. You can get away with it actually with log base 10 because it's on your calculator. Because the problem tends to be is what do you do when it's not that base? Are there things you can do? The answer is yes. All of them ends up being equally unpleasant.